Hello guys, how are you? Welcome to Maths Zone African Motives, your favorite channel. And today we are back again at grade 10 Physical Sciences. We are on a video series that is called Mechanics. So we agreed that we want to look at a broader topic that is mechanics that covers for term 3 as well as term 4. So we just want to start mechanics from the basics going to where it ends, unlike just starting at where someone would say maybe for term 4. We just want to start at the basics. So our first video was introducing mechanics, defining what mechanics is, and also getting to define physical quantities, and then classifying physical quantities into two broad groups, which are vector quantities and scalar quantities, as well as defining what a vector is, and then trying to determine how we can represent vectors and calculating what we refer to as a resultant vector using different methods, which are graphical as well as algebraic calculations. So if you missed out on our first video, please go check it out. Now we are on motion in one dimension, and then after motion in one dimension we are going to go to mechanical energy. So that is what houses what we refer to as the broader topic mechanics. So let's get started with mechanics. We want to start by defining what is motion in one dimension. So motion in one dimension is just motion in a straight line. It's either you are going forward or else you are going backwards. Or sometimes you might be going up or down. That is motion in a straight line. So when we say motion in a straight line, it's either you are on the horizontal axis or else you are on the vertical axis. So you can see that if you go up or else down, you are still in the same plane. If you go right or left, you are still in the same plane. So that is what we refer to as what motion in one dimension. So what is it useful for? So we get to know that it is useful for learning how to describe the movement of cars along straight roads or else trains along straight railway tracks. It helps us to calculate things like braking distance, the distance that might be required for you to brake, maybe before you actually get to hit on another car, or else you actually want to brake before the next red traffic light. So we use motion in one dimension calculations to help us to understand that, to help us understand the movement of cars along a straight road. Is it either accelerating or else is it moving at uniform motion? So now I want us to actually get to what? To start on our motion in one dimension. So for us to start describing or else learning about motion, we need to first describe what we refer to as frame of reference. We touched on this when we were doing vectors. A frame of reference is just a reference point or else a point of origin where you are starting. Let's say, for example, you want to move from point A to point C. We are saying that you are starting at point A. That is your origin or else your reference point. So whenever we are measuring motion or else whenever we want to dive deep into motion calculations, we need to first start by defining our frame of reference, stating where we are starting. So we get to say that the first thing to focus on when studying the motion of an object or else the motion of a person is their position. Where are they? So this describes the location where you are. For example, I would like to explain this using five friends. We have got Komau, Kolo, Cosma, Kogis, and Kelvin. So these 5 friends, they live in a neighborhood where their houses are situated next to each other, which is one after the other. And then at one end, there is on one end of their street, there is a school, and then on the other hand, there is a shop. Let's see that picture. So this is Komau's house, Kolo's house, Cosmos house, Kogis, and Kevin. And you can see that on the other end of the same street, there's a shop, and the other end of the same street, there's school. So at some point in time, we might want to determine the position of the what? Of the school. But for us to determine the position of the school, we need to determine our reference point. To what reference is this position situated at? For example, if I am to start with the what? With Kevin's house, I can actually get to say that the school is situated west of Kevin's house. Mean to say that the direction in which the school is situated, it will be in the westward direction to Kevin's house. But however, that is not enough. At some point in time, we need to know the straight line distance between the two. Meaning to say, if we are to say that Kevin actually left his house for school, we would necessarily need to know how much distance did he travel. So, like for example, here they said, determine the position of the school. Now, what you need to do, you need to first determine your reference point. So at some point in time, we will take Cosmos house as the reference point. So if this is the reference point, we are saying that this is our origin. So this is where we are starting. So origin simply means that the point where we are at, or else the point where we are beginning our journey. The point where our journey begins. So that's what an origin means, the point where our journey begins. So if we are to begin our journey from Cosmos house, we would actually be able to now determine the position of the school in reference to Cosmos house. So in reference to Cosmos house, we can see that if we are to determine our direction, so when we were doing vectors and scalar quantities, we actually agreed that when you are now representing vector quantities, you need to first start by defining what we refer to as the what? As the reference direction. So we can either use up, down, right or left, or else we can simply use the what? The compass, which is the easiest thing to use, which says north, east, south, and then what? West. So now if we want to know the position of the school, we would actually be positioning the school in reference to Cosmos house, because that is what we said, that's our what? That's our origin. So you would see that the school is in the westward direction. So the school is west of what? Of Cosmos house. But what is the distance between the school and what? And Cosmos house? You would say that there is 100 meters plus 100 meters plus another 100 meters. So this actually makes what? 300 meters from Cosmos house to the school. The distance that is in between there is what? It's 300 meters. So when you are now stating what we refer to as the position of the school, you would actually come to actually get to say that the school is 300 meters west of Cosmos house. So it will be what? 300 meters what? West of what? Of Cosmos house. Or else you might also come to choose to say, let my west be a negative and let my east be a what? Be a positive. So that you would know that when you are going in this direction, you have got positive direction. If you have got positive distance, sorry. If you are going in this direction, you have got what? Negative distance. So that from your origin, which is Cosmos House, the school will now be 100 meters plus 100 meters plus 100 meters, which is a negative 300 meters, which will simply tell you that if you say negative, that's west direction. And then the magnitude would be 300. So the position will simply be what? A negative 300 meters, or else 300 meters west of Cosmos House. So when we want to study the motion of objects, we need to first determine what we refer to as what? As the reference point. Where are we starting at? Once we have determined that, now we can now be able to describe our movement in terms of different features. And our different features, they fall under three classification, where we are saying we have position, we have speed, and we have got acceleration. What do we mean by that? You would see that position simply refers to the object's location. Where is our object located? That's our reference point. And then when let's get to say it's Cosmo. If Cosmo moves from his house to the school, it simply means that Cosmo has been displaced from his original position to a final destination. And that change in position is what we call displacement. So displacement is simply the change of location. So if you were at a location A and then you move to location B, let's say your final location is now B, it simply means that your displacement was actually what? The straight line movement between A and B. So we are saying the change in location from A to B. But however, though, you might not move in this straight line. But at some point in time, like we can see from this example of Cosmo, Cosmo might decide to leave for school. And then when he is now at Kolos' house, he might actually receive a call from his dad. And then he might need to return back. But remember, he had moved already to what? To Kolos' house. And then after returning back, maybe his dad wanted to give him pocket money. After giving, or else after receiving that money, he would actually get to return back and then head to school. So now you would see that his change in position was to say that initially he was at his house. But now his final position is at their school. So the location there, or else let's get to say that the position of Cosmo after all this scenario will now be what? It will now be simply negative 300 meters, or else 300 meters what? West. That is the straight line distance that is in between these 2 points. But how much distance did he cover? What was the total length that he moved from the moment that he left his house initially up until he reached the school? Even though he had been called back by his father, you would see that he moved 100 meters plus 100 meters back, which is now 200. And then he later moved another 300. So his total distance that he moved is 500 meters. That is the magnitude of the length that he covered. That magnitude of the length that he covered is what we refer to as what? As the total distance covered. So there is a difference between something that we refer to as displacement and something that we refer to as distance. Distance simply becomes the total length covered for each movement, whilst displacement becomes the change of location. Then, when we are describing our movement, we might also need to know what was the total time that was taken to cover this distance. And that actually relates to something that we refer to as what? As speed. to say that the total distance covered per unit time is what we refer to as what? As speed. And that becomes how fast someone would be moving or else an object is moving. And then at some moment in time, there is what we refer to as velocity. Now, velocity comes to be in relation to something that we refer to as what? As displacement, where we say that velocity tells you how fast you are changing your location, how fast the object is moving and where it is moving to. So velocity has direction as well as displacement, while speed and distance, they don't have what? Direction. We will look much more deeper into distance, displacement, speed, and velocity in this next slides to follow. Now we later go to something that comes to say acceleration. Acceleration tells us exactly how fast the object's speed is changing, or else the velocity speed is changing. Is our object speeding up or else it is slowing down? That is what acceleration tells us. So we can either describe our motion in terms of its position, to say that Cosmo was at his house and then he left for school in the morning. So initially he was at his house, but he left for school. So you know his movements by the location or else by the change in location. Or else you might actually get to describe the movement of Cosmo in terms of the speed, the total time he took to move from his house up until he reached to school. It tells you how fast he was moving. Or at some point in time, you might describe it in terms of what? Of how fast the speed is changing, which is was Cosmo speeding up or else was he slowing down? So after these features, we now need to know more and actually start defining them specifically each term by each term, and start classifying them as either vectors or scalar quantities. But at some point in time, you would see that we already did that when we were doing vectors and scalar quantities. So we'll just get to mention it in passing. So we say that distance is the total path taken. So you would need to know the total length within this total path that you moved. That is what we call distance. And distance depends on the path. It is always positive. You can never have a negative length. If someone moved, he moved a positive distance. And by that, it is a scalar quantity because it does not have any direction. You can see that here, at some point in time, this person was going up, and then he later went down, and then he went up, he later went down. So it is irregardless of what? Of direction. It is just the total path taken. And then now displacement becomes the change in position. Initially, he was here, which was at his school. Let's say that now he had knocked off. He started at the school and then he went backward to the shop. So you would see that the straight line path, or else let's get to say the straight line length between the school and the shop, that is what now becomes our displacement, the change in position. I was at school, now I'm at the shops. So the distance, the straight line distance in between the two becomes what? So you would see that displacement has got direction, because if I was at school, now I'm now east of what? Of my initial position. But when it comes to distance, I actually get to move haphazardly, irregardless of the direction. So here we calculate the length that is just in between the two positions, because we call displacement change in location. So if my initial location was 0 meters, and I call this direction positive, and now I'm now at 10 meters. It simply means that I've moved a displacement of what? Positive 10 meters. Because I know that my positive direction is in the eastward direction. So we can actually have a positive displacement and a negative displacement. For example, if going to the left, I get to choose it to be negative, it simply means that if I actually get to 10 from the shops and go back to school, it means that I'm now moving at a what? At a negative direction. So that if I had moved from school to the shops and then now I've came back to the school, it simply means that my final displacement, which we usually represent by S, is going to be equal to positive 10 plus a negative 10, which will be equal to 0. So I haven't been displaced. My initial position is still the same as my final. So displacement there is 0 if I had moved from school to the shops and back to the school. So that is how displacement works. So displacement is a vector. It has got both magnitude and direction, unlike distance, which just has got what? Magnitude only. Now let's go to speed and velocity. You would see that speed simply describes the total distance covered per unit time, which is to say that also speed is a scalar quantity, because in between distance and time, none of them are actually a what? A vector. So these, they will result in a scalar quantity. And this is how you calculate your average speed. And we say that speed depends on path taken, just like our what? Just like our distance. And it is also always positive. And we have mentioned that it's a scalar quantity. So speed does not depend on any direction. That is the reason why it is always positive. But when it comes to velocity, we say that velocity is the rate of change of our position. So change in position per unit time, for which position is direction. My original position becomes my reference point. If I change this position, I'm either changing it towards the east or else towards the west, towards the north or else towards the south. So it has got both magnitude and direction. The distance in between these 2 points and the direction in which I changed that position. Was I at A or else I was at B? I was at A going to B. So I have that direction to say I was going to B coming from A. And the distance that is in between A and B in a straight line is equal to. So we get to say that velocity now becomes to say the rate of change of this displacement. So that is the total straight line distance divided by the unit time taken to cover that displacement. So change in position per what? Per unit time. That is what we refer to as what? As velocity. And velocity is a vector, meaning to say that it has got both negative and positive. It can either be a positive value or else a negative value. It can either be towards the east or else towards the west. So direction can be determined from the sign convention used. For example, if you choose your east to be your positive, it simply means that if you later calculate and your final velocity is given as a positive 5 meters per second, it simply means that the velocity is towards the what? The east. So this is where we say that the direction of our velocity can be determined from the sign convention. And then acceleration is simply the measure of how fast the velocity of an object is changing. So if it is how fast the velocity is changing, we are simply saying change in velocity per unit time, or change in velocity divided by the change in time. So this is change in velocity, which can actually be final velocity minus initial velocity all over what? The total time that was taken for that change in velocity. That is what we refer to as acceleration. So acceleration is simply the rate of change of velocity, and it can be calculated in this way. So it determines if your object is speeding up or else it is slowing down. Now, when we are describing motion, we can either say that our motion is in uniform motion, which is having a constant velocity or constant speed. So once you hear what we refer to as uniform motion, once your motion is described as uniform, it simply means that the speed or the velocity of that object is constant. So an object moving with uniform velocity changes its position by the same amount in equal times. So it simply means that you move or else you change your velocity, which is 10 meters after every 2 seconds. You change your position 10 meters after every 2 seconds. So which means that if you were starting from maybe let's say point A here, and you ended at point B, or else let me say point D there. So from point A to point B, from point B to point C to point D, this is 10 meters in between A and B, 10 meters in between B and C, 10 meters in between C and D. The time that you are going to take to change position from A to B will be the same with the time that you are going to change your position from B to C, which would be if you moved, maybe if you took 2 seconds to change that position, you would also take 2 seconds to change position here. You would also get to take another 2 seconds to change the same position here. So this is where they are now saying that an object that is moving at uniform motion or else uniform velocity changes position by the same amount in equal time intervals. That is what they mean here. So when we are representing our uniform motion using velocity time graphs, you would actually get to see that the velocity time graph for motion with uniform velocity would be a horizontal graph because the velocity is constant. But if you are looking at a position time graph, your motion being of uniform velocity, it will always be a straight line. What do I mean by that? Let's look at the following graphs. This is a position time graph where you draw your position in your y-axis, and then you draw your time in your what? In your x-axis. So this is your y-axis, and then this becomes your what? Your x-axis. So your position is this side, your time is this side. So for uniform velocity, your graph for position time graph will always be a what? A straight line with constant gradient. So the gradient for the position time graph, so on a position versus time graph, the gradient, which is given by what? By delta x over delta t, simply means what? Velocity. I'm sure you can relate to say that, let's say I want to calculate this gradient. I would take to say that, let's say this one becomes my 0.2, this one being my 0.1. You know that if you want to calculate gradient, which you usually depict by m, we say y2 minus y1 over x2 minus x1, where we say the value of y2 minus the value of y1. So the value of y2 here would be what? It would be x value. So that is the position at point 2, position at point 1. And then the value here it would be actually the time at point 1 and the time at point what? At point 2. So you would see that this will relate to what? To x2 minus x1, where x refers to what? To position. And then divided by t2 over t1. This simply refers to what? To velocity, because we said velocity is the rate of change of position. So if you look at this equation, it simply tells you the rate of change of position. So the gradient under a position times graph, it gives you velocity. The gradient under a position time graph gives you velocity. And we said that since velocity would be constant, it simply means that the gradient of your position time graph has to be constant. So you would have a simple straight line with the equal gradient there, which is under uniform velocity. And then if you are to draw a velocity time graph where velocity is uniform, we are saying that velocity is constant. So the velocity value will remain the same. If you were moving at 1 meter per second, it will still be 1 meter per second up until you reach 3 hours or else 100 seconds. So it will be a horizontal straight line at a certain position or else at a certain level corresponding to the constant velocity. And then the acceleration time graph would be a constant zero line on your acceleration. So constant velocity or uniform velocity is equal to what? To zero acceleration. So you know that acceleration is given by v final minus v initial over the change in time. If v final is equal to v initial, this is where velocity is constant. It simply means that on top here I'll be having a 0. So my acceleration will simply go to become what? 0. So whenever I'm having uniform motion or else uniform velocity or uniform speed or constant speed, constant velocity, my acceleration is always 0. So I'll be having a constant 0 line for my acceleration time graph. So these are what we refer to as motion time graphs. So this is for uniform motion or else uniform velocity. So mind you, these words, they are used interchangeably. You have to master their meanings to say that uniform motion means what? Uniform velocity or else uniform speed or else constant velocity. Now let's go to what we refer to as uniform acceleration motion. So uniform acceleration motion, we are simply saying that the rate of change of velocity is constant after every time period. So the velocity is changing, but it is changing at a uniform rate. So uniform acceleration simply means that an object is moving with the same change or else the same rate of change of your what? Of your velocity. That is to say that the velocity changes its magnitude by the same amount in equal intervals. So maybe we can explain this better when we are using graphs, because you will see that a velocity time graph for uniform acceleration will always be a straight line. Why? Because under velocity time graph, the gradient gives you acceleration. So if the acceleration is the same, it simply means that the gradient has to be the same. So it will be a straight line graph of same gradient. And the gradient can either be positive or negative. And then for the position time graph, the graph is not going to be straight line, but it is going to be a curve, because we are saying that the velocity is changing, but it is changing uniformly. So that curve has to be smooth. But the acceleration time graph, the acceleration is what? The acceleration is just constant. So it will be horizontal, because we are saying that acceleration is not changing. Yes, it's accelerating, but at a same what? At the same value. So you would see that the position time graph, it's a smooth curve which is showing you that the velocity is changing, but with equal magnitude. That is why the velocity time graph would be having the same gradient here. So the acceleration time graph has to be horizontal because we are moving at the same constant acceleration value. So that is what we refer to as uniform acceleration. That is uniform rate of change of velocity. So those are the two different motion time graphs, or else two different ways of describing our motion within our syllabus. So this is a summary of our motion time graphs for different different scenarios. Let's say, for example, we've got an object which is stationary, that is not moving. Stationary simply means that there is no movement. So when you hear that an object is stationary, just know that its velocity is equal to 0. And its position will remain constant. So on our graph, position time graph, you see that the position will remain constant. So if I had already moved 5 meters, or else if I'm 5 meters away from my reference point, I will remain at that position for the time being. Mean to say that as the time is changing, I will be on the same position. That is what we mean by stationary. It might take 10 hours, so the time is changing, but I'm still at the same position. It's more like someone who wakes up in the morning, he bathes, and then he says that I'm going to work. But you will see that you will spend more than 8 hours while he's seated at the same position. He hasn't changed his position. So that is not work in terms of physical meaning, in terms of our physical science meaning. Work done has to do with change in position. You will learn that when you get to grade 12, when we are now defining work. But here I'm just giving you an example to say that that person would actually get to take 8 hours while he's on the same position. So he is stationary. His velocity is equal to 0. So the position time graph would be a horizontal constant line. But when it comes to velocity time graph, the velocity time graph would be a horizontal 0 line graph because the velocity there is 0, as well as the acceleration. When we are now under uniform motion, we described our graph to say that we'll be having a constant straight line graph with constant gradient. So the gradient here has to be it has to be constant. But velocity time graph, it has to be horizontal because the velocity here is also constant. And then the acceleration is 0 because the velocity is constant. And then when we are actually on motion with constant acceleration, when we are with motion with constant acceleration, this is where we say the position time graph, the curve it has to have a smooth curve. The line is no longer straight because the velocity is changing. It is increasing. Even though it is increasing at the same rate, it's no longer the same. Here the velocity is the same, so the gradient has to be the same. So here the gradient is increasing but at the same rate. That's why you would have a curve. But that curve, because we are increasing the gradient at the same rate, we need to actually get to to have a smooth curve. And then on your velocity time graph, you would have something like a straight line with a constant gradient because the acceleration is constant. Because the acceleration is constant, you would have a constant horizontal line. At some point in time, these graphs, they can be negative. So you need to have a simple and basic picture just like these ones. be able to draw this graph given different scenarios. Now, there is something under a velocity time graph. So we said under a position time graph, when we have position, so when x in meters versus time, just know that the gradient gives you what? Velocity. So the gradient on a position time graph gives you velocity. Nothing else. And then on the velocity time graph, the gradient gives you what? Acceleration. So the gradient gives you acceleration, but the area under this graph, the area is equal to the displacement. So just know that area under a velocity time graph gives you the total displacement. So the area under here would be given by half base times height. If you calculate that half base times height, you are going to get what? Displacement. So those are the key features of these graphs that you need to remember and to know. They usually like to ask you to actually calculate displacement under a velocity time graph. Just know that you need to calculate the total area under that graph if they say total displacement. Now, since we have described our motion in one dimension to be motion in a straight line, and we have given the features of how we describe that motion to say that it can either be uniform motion or uniform acceleration, and we have defined terms to do with the features of our description of our motion, which is position, displacement, distance, and then we said speed and velocity, and then we later said acceleration. Now we need to actually get to do with what we refer to as equations of motion or kinematic equations. These equations, they were readily determined for us. They help us to determine unknowns given a scenario. For example, they will say that a car, maybe let's get to say that a car moving at a velocity of 4 meters per second east actually takes 10 seconds to reach or else to cover to cover a distance of what? Of 10 meters. And then they will now get to say that the final velocity, or maybe let's get to say that this car, it is moving at 4 meters per second, and then it is moving eastward, and then it sees, maybe let's get to say, a red traffic light, which is a red robot. It needs to brake in 10 meters, meaning to say that its final velocity would be equal to 0. And then they tell you that it takes 10 seconds. They now get to ask you, what is the acceleration or deceleration of the car? You need to use what we refer to as what? As equations of motion. And what are these equations of motion? These equations of motion, they were already determined for us. The first one says that the final velocity is given by the initial velocity of the object plus the acceleration of that object times the total time taken. So if you know the initial velocity and you know the acceleration, you can calculate the time taken. Or else you can know the final velocity and then know the initial and then know the total time taken, but you do not know the acceleration. You can calculate that acceleration by just applying this equation. And then we go to the second equation. The second equation says that if you want to calculate your total displacement that has been moved, or else the change in position from point A to point B, which is the straight line distance there. If you know your initial velocity and the time it took to change that position, as well as the acceleration, you can simply calculate your change in position by saying V initial times the time taken plus half of the acceleration times the time taken squared. So it's all about applying logic in trying to determine what is it that I'm given and what is it that I need to find. And then the final equation says final velocity squared is equal to, here it was supposed to say initial velocity squared plus 2 times acceleration times the displacement. So if you know the displacement, the change in position, and the acceleration, and the initial velocity, you can simply calculate your final velocity. And this is usually for what? For average velocity, where we know that V average can be given by final velocity plus V initial over the time taken. Sorry, it's over 2 there. I'm now saying, I'm just copy. So we are saying that final velocity plus initial velocity divided by 2, it will give you the average velocity. Now, we know that we can actually also calculate our average velocity by saying the total displacement moved per unit time. The total displacement moved per unit time. So if we know the total displacement moved per unit time, we can equate these two and we'll end up having this equation, which is to say that the total displacement can also be calculated using an equation which says V final plus V initial divided by 2 times delta T. So these equations are the ones that we are going to be using as we are going forward. So this video is just an introduction to motion in one dimension. So the following videos would be about calculations using these equations of motion, as well as calculating whilst we are given description of our motion. So thank you guys for tuning in on our introduction video. Let's meet on on our next video, which has to do with calculations of motion in one dimension.